There is an experiment you can run in a lab today where the outcome of an event appears to depend on a decision made after the event has already occurred. The photon goes through the device, lands on the screen, and only then do you choose whether to check which path it took. And depending on what you choose, the pattern of where those photons landed changes. Not going forward, going back. The data already recorded shifts based on a choice that hadn't happened yet when the recording took place. This is not a hypothetical. It is not a misinterpretation of uncertain data. It has been repeated across multiple labs with multiple particle types, and the result is always the same. Your present decision is connected to a past event in a way that our best theories of causality cannot fully explain. And this is only one of several experiments and paradoxes that point at the same uncomfortable conclusion. We do not understand what is actually happening at the smallest level of physical reality. That is worth sitting with for a moment. Quantum mechanics is one of the most accurate and extensively tested scientific theories ever devised. It is the foundation of semiconductors, lasers, MRI scanners, and GPS satellites. Without it, the entire technological infrastructure of modern civilization collapses. The predictions are so precise that when physicists say the theory is correct, they mean correct to more decimal places than almost any other theory in the history of science. And yet, when you ask what the theory actually means, what is really going on beneath the equations, physicists disagree. Not on small details, on everything that matters. On whether particles have definite properties before measurement. On whether the universe branches into parallel versions every time a quantum event occurs. On whether consciousness plays a role in determining which outcome becomes real. On whether the past is fixed or is still being completed by what happens now. These are not fringe debates happening at the edge of physics. They are the central unresolved questions of the field, and they have been unresolved for nearly a century. To understand why, you need to understand what quantum mechanics actually says, and where the point of confusion begins. In the everyday world, things behave in ways that feel intuitive. A ball thrown across a room follows a predictable arc. A light switch flipped in a dark hallway produces light. If you want to know where something is, you look at it, and looking does not change the thing you are looking at. The universe feels like a machine running on fixed rules, and you are an observer watching from a safe distance. This is the framework that Newton and later Einstein formalized into the most successful physics of their time. Everything had a cause, everything produced an effect. The state of the universe at any moment followed from the state of the universe at the moment before. You could calculate where a cannonball would land, where a planet would be in 1,000 years, how a comet would arc through the solar system. The math was deterministic and the universe felt solid. Then, scientists started looking at very small things, and the framework began to break down. Not slightly, not in a way that could be patched with more equations or better instruments. Fundamentally, the rules that governed balls and planets and light switches simply did not apply to atoms and electrons and photons. And what replaced those rules was something that worked brilliantly in practice, but made almost no intuitive sense as a description of reality. The central feature of quantum mechanics is this: a particle does not have a definite position, speed, or state until you measure it. Before measurement, it is described by something called a wave function, which is a mathematical object encoding all the possible states the particle could be in, each with a certain probability. The particle is not secretly in one of those states, and you just do not know which one. It genuinely occupies all of them simultaneously. This is called superposition. When you measure the particle, something happens. The wave function collapses. The particle picks one outcome from the range of possibilities, and that becomes the result you record. The measurement has not revealed a fact that was already there. It has, in some sense, created the fact. That is already strange, but the strangeness compounds the deeper you push. Because the equations that describe how the wave function evolves over time, specifically the Schrödinger equation, do not include any mechanism for this collapse. They simply describe a wave function spreading out through all its possibilities, evolving smoothly and continuously. There is no moment in the math where the particle suddenly chooses. There is no built-in rule for when the probabilities snap into a single outcome. The collapse is added on top of the theory almost as an afterthought, because without it, the theory cannot connect its beautiful mathematics to the facts of what we actually measure. This is called the measurement problem, and it sits at the center of every confusion in quantum mechanics. It is not a problem that physicists have not thought about hard enough. It is a problem where every proposed solution turns out to create new problems of equal or greater severity. And what makes it even more unsettling is that the paradoxes it generates are not purely theoretical. They've been tested in real experiments, and the results keep confirming that something deeply unusual is happening. The giants of the field felt this deeply. Richard Feynman, one of the most brilliant physicists of the 20th century, said plainly that nobody understands quantum mechanics. Not as an admission of personal confusion, but as a statement about the collective state of the field. Niels Bohr, who did more than almost anyone to build quantum theory, said that anyone not shocked by it has not understood it. Erwin Schrödinger, whose equation is the backbone of the entire framework, said he regretted ever having anything to do with it. Albert Einstein spent the last decades of his life insisting the theory must be incomplete, because its implications violated every instinct he had about how the universe should behave. These were not people who had not studied the problem, they had built the problem, and still they could not explain what was really happening. Start with the experiment that opened this video. The delayed choice quantum eraser is a refined version of one of the most famous experiments in physics, the double slit. In the double slit setup, particles are fired one at a time through a barrier with two narrow openings. When no one checks which slit each particle goes through, the particles build up an interference pattern on the screen behind the barrier, the same kind of overlapping wave pattern you would see if you dropped two stones into a still pond. This indicates the particle traveled through both slits simultaneously, behaving like a wave interfering with itself. When you add a detector to check which slit the particle actually went through, the interference pattern disappears. The particle now behaves like a solid object passing through one slit only. The pattern shifts from wave behavior to particle behavior, and the only thing that changed was whether you were watching. This alone is unsettling enough. The act of observation changes the fundamental physical behavior of the particle, but the delayed choice quantum eraser goes further. In this version, you allow the particle to pass through the system and register its position on the screen before making any decision about whether to record which path it took. The particle has already arrived, the position has already been registered. Only after all of that do you decide whether to erase or preserve the which path information. When you choose to preserve the path information, the particles, analyzed after the fact, show no interference. When you choose to erase the path information after the particles have already hit the screen, the data shows an interference pattern. A decision made after the event determines which pattern the event produced. To be precise about what this means, you cannot use this to send information backward through time. The interference pattern only appears when you analyze the data in groups sorted by what you later decided to do with the path information. Any individual particle's position tells you nothing. Only the statistical pattern across many particles reveals the effect. So causality is not being violated in a way that allows time travel or retrocommunication. But the pattern itself, the fact that your post hoc decision about information determines whether interference occurred, is genuinely mysterious. Some physicists interpret this by saying the particle has no definite history until all relevant information is in place. Others suggest time itself is more flexible in the quantum domain than our daily experience implies. There is no consensus. What everyone agrees on is that this experiment reveals something real and profound about the relationship between time, information, and physical outcomes. The delayed choice eraser is connected to a broader idea called retrocausality. In classical physics, causes precede effects. The cannonball fires because the powder ignited, not the other way around. In retrocausal interpretations of quantum mechanics, this directionality is not guaranteed. Information can flow backward through time, not in a way that lets you change history, but in the sense that the final conditions of an event help determine its initial conditions. One formal version of this idea is called the two-state vector formalism. In this framework, a quantum system is not fully described by its state moving forward from the past. It is also described by a second wave function traveling backward from the future. The current state of the particle is shaped by both boundary conditions simultaneously, what it was doing at the beginning and what it ends up doing at the end. This does not break the mathematics of quantum mechanics. In fact, physicists have shown that retrocausal interpretations can reproduce all the standard predictions of the theory. What they cannot agree on is whether the retrocausality is a feature of reality or an artifact of how we construct the equations. That debate remains open. What makes the retrocausality discussion genuinely unsettling is its implication for the nature of time itself. If future events help determine past states, then the familiar arrow of time, the sense that the past is fixed and the future is open, may be an illusion generated by the scale at which we experience the world. On the quantum level, time might be more like a web of mutual dependencies than a river flowing in one direction. Some physicists extend this into a picture called the block universe, where time does not flow at all. The past, present, and future all exist equally as parts of a single four-dimensional structure. What you experience as the present moment is not time happening. It is your consciousness moving through a fixed landscape. Nothing changes. Everything simply is, spread across a geometry of spacetime that contains your birth and your death and everything in between as equally real slices of the same structure. If that is true, then asking what is happening now is no different from asking what is happening in Rome. The answer depends entirely on where you are standing. This connects directly to a second paradox, one that challenges not just the direction of time, but the very idea that there is one shared reality at all. In 1961, the physicist Eugene Wigner proposed a thought experiment that began as an extension of Schrödinger's famous cat scenario. Instead of a cat in a box, Wigner imagined a human being inside a sealed lab. This human, whom Wigner called his friend, is performing a quantum measurement, observing a particle that is in superposition between two states spin up and spin down. From inside the lab, the friend performs the measurement and sees a definite result. The superposition collapses. The particle is spin up. Reality has resolved. The friend writes down the result and waits. But Wigner is outside the lab. He has not seen the result. From his external perspective, the lab, including his friend and the measuring equipment, is a large quantum system that he has not observed. According to the rules of quantum mechanics, an unobserved system evolves in superposition. So, from Wigner's point of view, the lab exists in a superposition of states, one in which the friend saw spin up and one in which the friend saw spin down. The friend has a definite experience. Wigner has a superposition. Both are applying quantum mechanics correctly, and yet they cannot both be describing the same reality. For decades, this was treated as an interesting thought experiment, but not a practical problem, because you cannot actually put a person into quantum superposition. The interactions between a human body and its environment are so numerous and rapid that any quantum behavior washes out almost instantly through a process called decoherence. The human is so entangled with everything around them that treating them as a pure quantum system is not feasible. But in 2019, a study published in Nature Communications demonstrated a simplified version of this paradox using particles and detectors rather than people. Two observers recorded different measurement outcomes for what was in principle the same quantum event. These were not differences in interpretation, they were differences in recorded physical outcomes. Within each observer's consistent framework, their result was correct, and the results disagreed. This experimental confirmation of the Wigner's friend scenario has no clean resolution under any existing interpretation of quantum mechanics. The many worlds view handles it by saying each observer experiences a different branch of reality, so there is no true contradiction, only the appearance of one from within each branch. The Copenhagen interpretation handles it by simply refusing to ask what is happening when no measurement is taking place. Other interpretations handle it by restricting what it means to make objective claims about quantum systems. None of these is fully satisfying, and the question that Wigner's friend raises refuses to go away. Is there a single objective reality, or is reality observer-dependent at a fundamental level? If it is observer-dependent, then science's core assumption of objectivity, that experiments produce facts that hold true regardless of who is observing, becomes far more complicated than anyone would prefer. This question connects directly to a phenomenon that sounds even more impossible: quantum pseudo-telepathy. Imagine you and another person are placed in separate rooms with no way to communicate. Each of you is asked a series of questions at random and must answer yes or no. If your answers match in a certain way, you both win. If not, you lose. The specific rules of the coordination game are set up so that without communication, a perfect classical strategy is impossible. No matter what pattern you agree on ahead of time, there will always be question combinations where your pre-coded answers fail to produce the correct coordination. But if you and the other person each hold one particle from a pair of entangled particles, something changes. You both make your yes or no choices by performing quantum measurements on your particles. You still have no communication during the game. no messages, no signals, no hidden information being passed back and forth. And yet when the game ends and your answers are compared, they match in ways that no classical strategy could have produced. This has been demonstrated in real laboratories using real entangled particles. The success rate in these quantum coordination games exceeds what is mathematically possible through any classical method. It is not a statistical fluctuation. It is a robust, reproducible result that has been verified across multiple experimental designs. The name pseudo-telepathy captures the strangeness. It looks like the two players are coordinating, like information is somehow passing between them, but nothing is being transmitted. The entangled particles are not sending signals. The rules of special relativity are not being broken. What is happening instead is that the two particles, despite being spatially separated, are part of a single quantum system. They are described by one wave function. Their properties are correlated not because information passed between them, but because they were never truly independent to begin with. One of the most elegant demonstrations of this is the Magic Square game. Two players must independently fill in rows of a grid with specific values following certain rules. Without quantum assistance, there is no strategy that guarantees success every time. With entangled particles and appropriately chosen quantum measurements, the players can achieve perfect coordination in a mathematically provable way. Another demonstration involves 3 entangled particles and 3 players, in a configuration first studied by the physicists Daniel Greenberger, Michael Horn, and Anton Zeilinger. In the GHZ setup, 3 players in 3 separate rooms can produce answers that cannot be explained by any local hidden variable theory, meaning no framework in which each particle carries predefined properties that it simply reveals during measurement. The correlations are too strong, too specific, and too consistent to have arisen from anything concealed in the particles ahead of time. Einstein found this deeply troubling. He called it spooky action at a distance and believed it indicated the theory was incomplete. He thought there must be hidden variables, predefined answers built into the particles that we simply had not yet discovered, which would explain the correlations without requiring genuine non-locality. But experiments have consistently ruled this out. The correlations seen in entangled systems are real and cannot be reproduced by any local hidden variable model. The universe is genuinely non-local in some sense that we are still working to fully characterize. What quantum pseudo-telepathy makes concrete is the question of what it means for two things to be separate. In classical physics, separation in space means independence. Two objects far apart influence each other only through physical signals traveling through the space between them. In quantum mechanics, entangled objects share a single description no matter how far apart they are. Measuring one instantly constrains what you will find when you measure the other, not because a signal traveled, but because the two were never fully separate objects to begin with. This does not tell us what the non-locality means at a deeper level. It does not tell us whether there is some underlying structure that makes the correlations possible, or whether the universe simply is fundamentally non-local in a way that has no further explanation. It just shows us that our intuition about separation and independence breaks down at the quantum level. Now consider what happens when you try to separate not two objects, but an object from its own properties. There is an experiment called the quantum Cheshire cat, named after the character in Lewis Carroll's story who gradually disappears until only the grin remains floating in the air. The name is apt in a way that feels almost too on the nose, because the experiment appears to demonstrate exactly that, a particle and one of its defining properties traveling through an apparatus by separate routes. The setup uses neutrons and a device called an interferometer, which splits a particle's path into two possible routes and then recombines them. When you put a neutron into this interferometer, quantum mechanics places it in a superposition of both paths simultaneously. This is standard behavior. What is not standard is what happens when you design the measurement scheme carefully enough to independently probe where the neutron's position is detected and where its spin, an intrinsic quantum property, is detected. The experiment uses a technique called weak measurement, which extracts partial statistical information from a quantum system without fully forcing it into a definite state. When you accumulate enough weak measurements from many runs of the experiment, a picture emerges. The neutron's position appears in one arm of the interferometer. The neutron's spin appears in the other arm. The particle went one way, its spin went another. In classical physics, this is incoherent. A spinning top does not leave its spin behind when it moves across a table. Properties are not separable from the objects that have them. An object's mass goes where the object goes. An object's temperature goes where the object goes. There is no mechanism by which one property could depart from the whole and travel independently. But in the quantum Cheshire cat experiment, that appears to be exactly what is happening. Some physicists interpret this as revealing that quantum objects are not objects in the classical sense at all. They are not discrete entities carrying a bundle of properties through space. They are more like nodes of interconnected probabilities, and those probabilities can be arranged in ways that separate what we would normally consider parts of a single thing. Others interpret the weak measurement results more cautiously, arguing that what looks like a separation is a mathematical artifact of how the measurement scheme works, not evidence of a literal spatial separation between particle and property. The debate reflects a deeper disagreement about how seriously to take the picture that quantum measurements paint. What is not in dispute is that the experimental results are consistent with the quantum Cheshire cat phenomenon. The spin is systematically detected on one side of the interferometer and the position on the other. Whatever philosophical interpretation you attach to it, the data is real. If a particle's properties can be interrogated separately in different regions of space, then questions about what it means to be a single unified object become suddenly complicated. Is a neutron a thing? Or is it a collection of quantum properties that happen to be correlated in ordinary circumstances but can, under the right conditions, drift apart? These questions lead naturally to one of the strangest thought experiments in all of physics, one that combines the many worlds interpretation with the problem of conscious experience in a way that is deeply uncomfortable once you fully work through the implications. The quantum suicide thought experiment begins with the many worlds interpretation, which is one of the most taken seriously solutions to the measurement problem. In the many worlds view, the wave function never collapses. Instead, every time a quantum event occurs with multiple possible outcomes, the universe branches. Every outcome happens, but in separate, non-communicating versions of reality. When Schrödinger's cat is in its box, the universe splits into a version where the cat is alive and a version where it is dead. Both are equally real. The cat in one branch does not know about the cat in the other. This interpretation has certain advantages. It removes the need for collapse as a special process. It treats the wave function as literally real rather than as a calculating tool, and it reproduces all the same predictions as standard quantum mechanics. It also has certain costs, the most obvious of which is the wild proliferation of unobservable parallel universes. The quantum suicide thought experiment takes this seriously and asks what it implies for a conscious observer facing a potentially fatal quantum event. Imagine a device connected to a quantum trigger, some measurement that has a 50% chance of producing outcome A and a 50% chance of outcome B. In outcome A, nothing happens. In outcome B, the device fires a lethal mechanism directed at the person operating it. The trigger is purely quantum, not probabilistic in any classical sense, but genuinely undetermined by prior conditions. The person presses the trigger. In the many worlds view, both outcomes occur. In one branch, outcome A happens and the person survives. In another branch, outcome B happens and the person does not. Now here is the crucial part. The person can only have a continued experience in the branch where they survived. Consciousness, whatever it is, can only follow the thread of experience through branches where the observer continues to exist. There is no experience of outcome B from the first-person perspective. There is no moment where the observer perceives their own discontinuation, because perception requires a perceiver, and the perceiver only exists in the survival branch. So, from the first-person perspective, regardless of how many times the experiment is repeated, the observer always survives. They always find themselves in the branch where outcome A occurred. No matter how improbable that branch becomes as the experiment is iterated, there is always some branch where the observer has survived every trial, and that is the branch their experience must follow. This is called quantum immortality. The idea that if many worlds is correct, and if consciousness must always find itself in the branch where it continues to exist, then from the inside, no conscious observer can ever reach a terminus. They will always find themselves surviving, even when the probability of survival becomes vanishingly small across the full branching structure. From the outside, other observers in other branches would see different things. They would witness some branches where their colleague survived all trials and other branches where the colleague did not. The first-person perspective of the survivor cannot be reconciled with the third-person statistical picture observed from outside. This thought experiment does not require any new physics. It is a logical extension of existing quantum mechanics applied to conscious observers. What it reveals is how little quantum mechanics actually tells us about the relationship between physics and first-person experience. The theory handles particles and probabilities with extraordinary precision. It says almost nothing coherent about what it means to be the person running the experiment. Questions about which branch you experience, why you find yourself in this branch rather than another, and what it would even mean to be simultaneously in all branches are questions that quantum mechanics, as currently formulated, simply does not answer. Some physicists treat this as evidence that the many worlds interpretation, despite its mathematical elegance, cannot be the whole story. Others embrace quantum immortality as a genuine prediction of the theory and note that it is not falsifiable, because any observer capable of reporting their results is by definition a survivor. Still others argue that consciousness is not a feature of quantum mechanics at all, and that the thought experiment is simply misapplying the framework to something it was never designed to describe. None of these responses is fully adequate. The discomfort remains. And then there is the black hole information paradox, which turns the discomfort into a direct conflict between two of the most successful theories in the history of physics. Black holes are, in their basic description, simple objects. Despite the enormous complexity of what creates them, a collapsing star with a specific mass, rotation rate, composition, and history, general relativity says that once a black hole is formed, only three numbers describe it completely: its mass, its electric charge, and its spin. Everything else about the object that fell in, the arrangement of atoms, the chemical composition, the information that distinguished one configuration of matter from another, is gone. The black hole does not remember what it ate, it just has a mass. This is called the no-hair theorem, and it follows straightforwardly from the equations of general relativity. A black hole is the most information-destroying object in the universe. Quantum mechanics says this is impossible. In quantum mechanics, information is conserved as a fundamental principle. When a quantum system evolves, its wave function changes, but the evolution is reversible. If you know the final state of the system and all the rules, you can in principle reconstruct any earlier state. Information does not disappear. It gets scrambled, spread out, encoded in correlations too complex to easily decode, but it is always there. If it were not, the basic mathematical framework of quantum mechanics would break down. Mendelian, the unitarity of quantum evolution, the property that probabilities always sum to 1, and that the evolution is invertible, would be violated. These two principles sit in direct opposition when applied to black holes. In the 1970s, Stephen Hawking calculated that black holes are not, in fact, completely black. Quantum effects near the event horizon cause pairs of virtual particles to appear spontaneously. Occasionally, one particle of the pair falls into the black hole, while the other escapes. Over an extraordinarily long time, this process drains energy from the black hole through what is now called Hawking radiation, and the black hole gradually evaporates and disappears. The problem is that Hawking radiation, as originally calculated, carries no information about what fell into the black hole. It is thermal radiation, essentially random, containing no record of the matter that produced it. If the black hole evaporates completely and the radiation is information-free, then the information about everything that fell in is simply gone. This is called the black hole information paradox, and it has been one of the central unsolved problems in theoretical physics for more than 50 years. Several solutions have been proposed, and each one trades one problem for another. One proposal suggests that the information is indeed encoded in the Hawking radiation, but in an extraordinarily subtle and complex way, hidden in quantum correlations between photons emitted at different times. If you had perfect knowledge of all the radiation ever emitted by an evaporating black hole, you could in principle reconstruct what fell in. This is sometimes called the Page curve solution, after physicist Don Page, who calculated what an information-preserving evaporation would look like. But demonstrating that the radiation actually contains this information in practice requires understanding the quantum geometry of the black hole interior in a level of detail that current theories cannot provide. Another proposal involves the holographic principle, an idea that emerged from string theory and was developed in detail by physicists including Leonard Susskind and Juan Maldacena. The holographic principle suggests that all the information contained in a three-dimensional region of space can be completely encoded on the two-dimensional boundary of that region, like a three-dimensional image encoded on a flat holographic film. Applied to black holes, this implies that information about infalling matter is not lost inside the black hole, but is encoded on the event horizon, the two-dimensional surface at the boundary of the black hole, and is eventually returned to the universe through the Hawking radiation as the horizon area shrinks during evaporation. This framework has strong mathematical support in a specific context, a particular type of spacetime geometry used in theoretical physics called anti-de Sitter space. In that context, a duality exists between a theory of gravity in the bulk of the space and a quantum theory with no gravity on the boundary, and information is demonstrably conserved. Whether this applies to black holes in the actual universe is less certain. A third proposal is the firewall paradox, proposed in 2012 by Ahmed Almheri and colleagues. This argument suggests that if information is truly preserved in the Hawking radiation, then the region just outside the event horizon must be dramatically different from what general relativity predicts. General relativity says that an observer falling into a black hole should notice nothing unusual at the event horizon. Space-time at that location is smooth, and the transition from outside to inside should be unremarkable. But if information is being preserved, the firewall argument shows that quantum correlations at the horizon must be structured in a way that creates an intense burst of energy, a wall of high-energy quanta that would incinerate anything passing through. This resolves the information paradox, but violates one of the central principles of general relativity, the equivalence principle, which says that freefall in a gravitational field should be locally indistinguishable from floating in empty space. Every proposed solution to the black hole information paradox preserves something and breaks something else. There is no solution that keeps everything intact. This is precisely what makes the paradox so significant. It is not a puzzle waiting for a clever trick. It is a sign that our two best theories of the universe are fundamentally incompatible, and we are missing something big enough to reconcile them. The missing piece might be a theory of quantum gravity, an account of how quantum mechanics and general relativity fit together in regimes where both matter. Such a theory does not yet exist. String theory is a candidate, loop quantum gravity is another, but neither has been experimentally confirmed, and neither has produced a complete resolution of the information paradox that everyone finds satisfactory. What makes this all even more striking is that every one of these paradoxes, the delayed choice eraser, Wigner's friend, quantum pseudo-telepathy, the quantum Cheshire cat, quantum suicide, and the black hole information paradox, points to the same unresolved core. We do not know what measurement is. That is the measurement problem in its most fundamental form. In quantum mechanics, a system evolves in superposition, and measurement produces a definite outcome. The theory is extraordinarily precise about probabilities before measurement and exact about what you will observe after measurement. It says essentially nothing coherent about what happens during measurement, about what actually collapses the wave function, about why you see one outcome instead of a blur of all of them, about what counts as a measurement in the first place. Does a photon detector count? Does a bacterium? Does a human? Does a sufficiently large classical system? Does a conscious observer? The Copenhagen interpretation, historically the most widely taught version of quantum mechanics, sidesteps this question by simply refusing to ask what is happening when no measurement is being made. The wave function is a tool for calculating what you will observe. Questions about what exists between observations are declared meaningless. This is pragmatically effective and philosophically unsatisfying. The many worlds interpretation answers the question by saying the wave function never collapses, all outcomes happen, the observer splits. But then you have to explain why you experience only one outcome, which pushes the problem into the territory of consciousness and identity, where physics has very few tools. Decoherence, the process by which quantum systems lose their interference properties through interaction with the environment, explains why we never see superpositions of everyday objects. Once a quantum system interacts with even a few air molecules, the quantum correlations that allow interference are distributed across so many particles that they become impossible to observe. The system effectively behaves classically, but decoherence does not tell you why only one outcome ends up in your experience. It tells you why the other outcomes stop being observable, not why they stop being real. Objective collapse theories propose that the collapse is a genuine physical process that happens spontaneously, similar to radioactive decay, and that large systems collapse faster than small ones. These theories modify the Schrödinger equation by adding a term that drives superpositions toward definite outcomes at a rate that scales with the number of particles involved. An electron in superposition takes an astronomically long time to collapse on its own. A human in superposition would collapse essentially instantaneously. This is appealing because it restores a single definite reality without invoking observers or consciousness. But no spontaneous collapse has ever been directly detected, and the specific mechanism remains unknown. And then there is the proposal that consciousness plays a role, that the wave function collapses when and only when it is observed by a conscious mind. This view is unpopular among most physicists for several reasons. It is vague about what consciousness is, it introduces a non-physical entity into an otherwise physical theory, and it seems to get the relationship backward, with consciousness determining physical reality rather than the other way around. But it keeps resurfacing because nobody has found a better explanation for why you always experience a single definite outcome rather than a superposition of many. The measurement problem is not just a technical issue for physicists to resolve. It is a question about what kind of universe we live in. Is reality a fixed structure that exists independently of observers, fully determined in all its details, waiting to be discovered? Or is reality something that crystallizes in the act of interaction, where properties do not exist independently of the processes that reveal them? These are not questions that quantum mechanics answers. They are questions that quantum mechanics forces into view by working perfectly in every technical respect while leaving the fundamental picture of what is happening entirely ambiguous. The paradoxes we have covered are not failures of physics, they are the evidence that physics is working correctly. They show us exactly where the current theories reach their limits. The delayed choice eraser exposes the limits of our understanding of time and information. Wigner's friend exposes the limits of objectivity. Quantum pseudo-telepathy exposes the limits of locality. The quantum Cheshire cat exposes the limits of our concept of an object. Quantum suicide exposes the limits of the relationship between physics and experience. The black hole information paradox exposes the limits of our ability to unify the two greatest theories of the 20th century. Every major advance in physics has been preceded by a paradox that the old theory could not resolve. Newton's laws emerged from questions about planetary motion that no previous framework could answer. Special relativity emerged from an inconsistency in the equations of electromagnetism when applied to moving observers. General relativity emerged from questions about what it means for gravity to act instantaneously at a distance. Quantum mechanics itself emerged from classical physics being unable to explain the spectrum of light emitted by heated objects and the behavior of electrons in metals. In each case, the paradox was not a sign that the old theory was wrong about everything. It was a sign that the old theory was missing something essential, and that a deeper and more accurate account was waiting to be discovered. This is the most plausible interpretation of where we are now. Quantum mechanics is not wrong. Its predictions are too accurate and too consistently verified for that to be possible, but it may be incomplete. It may be a limiting case of something deeper, a more fundamental theory that explains not just what quantum systems do, but why they behave the way they do. A theory that shows why superposition is a feature of small systems, but not of large ones. A theory that specifies exactly what measurement is without requiring the concept to be dropped in from outside the formalism. A theory that reconciles quantum mechanics and general relativity, eliminating the black hole information paradox not by patching one or the other, but by replacing both with something more complete. What that theory looks like, nobody currently knows. Some researchers are pursuing quantum gravity through frameworks like loop quantum gravity or string theory. Others are developing new formalisms for quantum foundations that try to derive the rules of quantum mechanics from more basic principles about information and probability. Others are investigating whether the quantum world might be understood in terms of relationships rather than things, where the properties of a system are always defined relative to another system rather than existing independently. Some of the most striking recent work involves the intersection of quantum information theory and quantum gravity. Researchers have found mathematical connections between the entanglement structure of quantum states and the geometry of spacetime, suggesting that space itself might be a consequence of quantum entanglement rather than the stage on which quantum events play out. If that is correct, then the entire picture of reality that we have inherited from classical physics, a container called space filled with things called particles, may be a derived approximation of something far more abstract. The honest answer is that we do not know what comes next. The paradoxes are real and unresolved. The experiments keep confirming that the universe behaves in ways that defy every intuition built up from everyday experience. And the deepest questions: what is measurement? Is reality objective? How does the quantum world produce? The classical world we observe? What happens to information inside a black hole? Are still open. What we can say is that the questions are real, the experiments are real, and the scientists asking them are not confused or incompetent. They are standing at the edge of what human knowledge currently understands and looking at something that does not yet fit into any framework anyone has built. That is uncomfortable. But it is also, in the deepest sense, what science actually looks like when it is working. Not a confident recitation of established facts, but a sustained confrontation with things that do not make sense yet. The quantum world is not refusing to be understood because it is fundamentally beyond comprehension. It is resisting the frameworks we have built because those frameworks were constructed from observations at a scale where quantum effects do not show up. We have been trying to describe a universe that operates on principles we only discovered in the 20th century, using intuitions built over millions of years of evolution in a world where those principles are invisible. It should not be surprising that this is hard. What is surprising is how far we have gotten. We have built devices that exploit quantum effects to perform computations no classical system could match. We have tested the predictions of quantum mechanics to extraordinary precision using experiments that would have seemed like magic to scientists a century ago. We have mapped the large-scale structure of a universe born nearly 14 billion years ago and identified the forces that govern its smallest constituents. And still, the paradoxes remain. They remain because they are pointing at something real, something we have not yet seen clearly, a feature of the universe that the current mathematics is too blunt to capture, or that our concepts are too limited to fully grasp, or that simply requires a new mode of thinking that nobody has invented yet. Every one of the paradoxes we have covered ends in the same place, not with an answer, but with a better question, not with a resolved picture, but with a sharper view of exactly what is missing. And that is precisely the kind of thing that, in the history of physics, has always preceded a breakthrough. We do not know when the next breakthrough will come. We do not know what shape it will take, or whose work will produce it, or whether the framework it requires has even been conceived of yet. What we do know is that the questions are precisely stated, the experiments are real, and the universe is waiting to be understood more deeply than it currently is. That is not a reason for frustration, it is a reason to keep looking. And if you are the kind of person who finds the looking interesting regardless of the destination, the quantum world will never run out of things to surprise you. If you found this exploration useful, consider liking and subscribing so you do not miss what comes next. There is more territory to cover, and the questions only get more interesting the further in you go. To fully appreciate why these paradoxes are so persistent, it helps to understand the history of how quantum mechanics was discovered, because the discomfort was built in from the very beginning. The theory was not constructed by a single person working from a unified vision. It was assembled, piece by urgent piece, by many scientists trying to explain experimental results that simply could not be reconciled with the physics of their time. The first crisis came in the late 1800s, when physicists were trying to calculate the spectrum of light emitted by an object heated to a glowing temperature. The classical theory predicted something called the ultraviolet catastrophe. As you move toward shorter and shorter wavelengths of light, the predicted intensity of the emission should rise without limit, going to infinity. Obviously, hot objects do not radiate infinite energy. Something was deeply wrong with the classical picture. In 1900, Max Planck found a mathematical formula that matched the actual observed spectrum. But to derive it, he had to make an assumption that he himself found bizarre, that energy was emitted not continuously, but in discrete chunks. Little packets. He called these quanta, from the Latin word for how much. Planck thought this was a mathematical trick, a calculation tool that happened to work but did not reflect any real feature of the world. He spent years trying to find a way to get the same result without the discrete packets. He never succeeded. 5 years later, Albert Einstein used Planck's quanta to explain the photoelectric effect, a phenomenon where light hitting a metal surface ejects electrons, but only if the light exceeds a certain frequency, regardless of how intense the light is. If light were a continuous wave, as classical physics assumed, intense light at any frequency should eventually eject electrons. But it did not. Only light above a threshold frequency worked, instantly, even at very low intensity. Einstein showed that this made sense if light itself traveled in discrete packets, what we now call photons. A single photon of the right frequency carried enough energy to eject an electron. A billion photons of the wrong frequency carried no individual packet energetic enough to do anything. This was a radical claim. Maxwell's equations, which described light as a continuous electromagnetic wave, were among the most successful pieces of physics ever assembled. They predicted radio waves, correctly described optics, and formed the basis of all electrical technology. And now Einstein was saying light was also a particle? How could both be true? That question turned out to be one of the central questions of quantum mechanics, and it still does not have a satisfying classical answer. Light exhibits both wave behavior, producing interference patterns, and particle behavior, arriving in individual discrete packets. Electrons do the same. So does every other quantum entity. They are not waves in the classical sense, and they are not particles in the classical sense. They are something else for which ordinary language has no good word. The word quantum particle is used, but it is really just a label for something that does not fit any familiar concept. Niels Bohr developed a partial model of the atom that used quantum ideas to explain why atoms were stable and why they emitted light at specific frequencies rather than a continuous spectrum. In Bohr's model, electrons could only occupy certain allowed orbits around the nucleus, and they emitted or absorbed a photon of a specific energy when they jumped between orbits. This worked remarkably well for hydrogen, the simplest atom. It worked less well for more complex atoms, and not at all in certain situations that required a full quantum treatment. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Max Born, and others then spent the 1920s building the full mathematical framework of quantum mechanics. Two different mathematical formalisms were developed almost simultaneously: Heisenberg's matrix mechanics and Schrödinger's wave mechanics. They looked completely different, but Paul Dirac and others proved they were mathematically equivalent. Two different ways of describing the same physics. The price of this success was conceptual. The theory worked, but nobody could agree on what it was saying about reality. The debates between Bohr and Einstein at the Solvay conferences in the 1920s and 30s became legendary. Einstein kept constructing thought experiments designed to show that quantum mechanics was either incomplete or inconsistent. Bohr kept finding refutations. The exchange sharpened both positions but resolved nothing. The most famous of these thought experiments was proposed by Einstein, Boris Podolsky, and Nathan Rosen in 1935. The EPR paper, as it became known, argued that quantum mechanics must be incomplete because it implied that two particles could be correlated in a way that seemed to require either faster-than-light signaling or the existence of hidden variables that the theory did not account for. Einstein, Podolsky, and Rosen thought this was a reductio ad absurdum, a demonstration that something was wrong with the theory. They expected that a more complete theory would eventually be found that explained the correlations without these troubling implications. They were half right. The more complete theory has not been found. But the troubling implications turned out to be real features of the universe rather than signs of a theoretical flaw. The resolution came from a physicist named John Bell in 1964. Bell proved a theorem that drew a sharp mathematical boundary between what quantum mechanics predicted and what any hidden variable theory could predict. If particles had definite properties encoded in advance, then certain statistical correlations between measurements would be constrained. Bell derived exact inequalities specifying the maximum correlations that any local hidden variable theory could produce. Quantum mechanics predicted correlations that exceeded those limits. This was experimentally testable, and the experiments, beginning with pioneering work by John Clauser in the early 1970s and refined dramatically by Alan Aspect in the early 1980s, and then by increasingly precise measurements over the following decades, showed consistently that the quantum mechanical predictions were right and the Bell inequalities were violated. The universe produces correlations that are too strong to be explained by any theory in which particles carry predefined hidden properties and influences travel no faster than light. Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics in 2022 specifically for this work. The experimental confirmation of Bell inequality violations is one of the most significant results in the history of physics, precisely because it tells us not just that quantum mechanics is correct, but that the universe is fundamentally different from any classical picture. The world is either not local, meaning influences can travel faster than light in some sense, or not realistic, meaning particles do not have definite properties before measurement, or both. Neither option fits comfortably into everyday intuition. And yet the experiments leave no room for escape. What this means in practice is that the entanglement experiments and the pseudo-telepathy games we discussed are not just abstract demonstrations of unusual physics. They are proof that the universe at its most fundamental level operates by rules that cannot be explained by thinking of particles as small classical objects with hidden properties being carried around through space. The quantum description, with all its counterintuitive features, is the most accurate description we have of what actually happens. This makes the measurement problem even more pressing. If particles do not have definite properties before measurement, then what does measurement do? Why does measurement produce a definite result? And what constitutes a measurement? These questions are not peripheral. They are at the center of what quantum mechanics says about reality, and they remain, after nearly a century of intense work, unresolved. One perspective that has gained serious attention in recent years is relational quantum mechanics, developed by the physicist Carlo Rovelli. In Rovelli's framework, quantum states do not have absolute values. They are always defined relative to another system. The state of a particle is not a feature of the particle itself, but of the relationship between the particle and whatever system is interacting with it. Different systems can have different, mutually consistent descriptions of the same quantum object because what they are describing is their own relationship to that object, not an absolute fact about the object. This dissolves some of the tension in the Wigner's friend paradox, because it acknowledges from the start that the friend and Wigner can have different descriptions without contradiction. They are each describing their own relational state. When they eventually compare notes, the comparison itself is a new interaction that produces a new relational state consistent with both previous descriptions. Whether this represents genuine progress or simply relocates the mystery depends on how you evaluate what a scientific explanation ought to do. Relational quantum mechanics is mathematically consistent and makes no new empirical predictions that differ from standard quantum mechanics. Whether it provides a satisfying account of what is actually happening or simply rephrases the problem in new language is a matter of genuine debate among physicists and philosophers of physics. A related approach comes from quantum information theory, which recasts the fundamental objects of physics not as particles or fields, but as information. In this view, what quantum mechanics is really about is not little balls bouncing around, but the structure of possible observations and the correlations between them. Particles are not things that carry information. They are patterns in a fabric of information that can be detected in various ways depending on how you interact with them. This perspective underlies much of the work on quantum computing, quantum cryptography, and quantum communication that has driven enormous advances in technology over the past 3 decades. It also provides a natural language for discussing the black hole information paradox, where the question becomes not whether physical matter went, but whether the pattern of information that described the infalling matter can be recovered from the outgoing radiation. Information theoretic approaches to physics are increasingly influential, and some researchers believe they point toward the correct path for unifying quantum mechanics and general relativity. The idea that space-time itself might be emergent from quantum information, that the geometry of space and time is a consequence of entanglement structure rather than a background in which events occur, is one of the most actively pursued ideas in quantum gravity today. The specific proposal, developed by Mark van Ramsdonk and others, is that regions of spacetime that are connected, meaning that you can travel between them, correspond to quantum systems that are entangled. When the entanglement between two quantum systems decreases, the spatial connection between the corresponding regions of spacetime weakens. At zero entanglement, the regions become disconnected, effectively separate universes. The connectivity of spacetime, what we think of as the geometry of space, is a manifestation of quantum entanglement. This is not yet a complete theory, and its domain of applicability is still unclear, but it represents the kind of conceptual shift that might be necessary to reconcile the paradoxes. If spacetime is not fundamental but derived, then questions about what happens inside black holes or what information means in the context of Hawking radiation might have cleaner answers in the underlying quantum description than in the emergent geometric description. The challenge is that the emergent picture only works cleanly in spaces with particular geometric properties that do not match the actual universe we inhabit. Extending the framework to cosmologically realistic spacetimes is an active area of research without resolved answers. Meanwhile, other researchers are taking a different approach, questioning not the relationship between quantum mechanics and gravity, but the quantum mechanical formalism itself. Some physicists believe that the measurement problem points to the need for a modification of quantum mechanics, not just a reinterpretation of the existing theory. Objective collapse theories, mentioned earlier, are one version of this. They propose that the Schrödinger equation is not quite right, that there is an additional physical process that causes wave functions to collapse spontaneously, and that this process becomes significant only for large numbers of particles, which is why we never see superpositions at the human scale. Experiments are now precise enough to test some of these predictions. If collapse is a physical process, it should leave signatures in the statistics of quantum measurements on large molecules or in the noise characteristics of sensitive detectors. Groups around the world are running experiments specifically designed to detect or rule out various collapse models. So far, no conclusive signal has been found, but the experiments continue to improve. There is also work on reformulating quantum mechanics from axioms that are more operationally grounded, deriving the rules of the theory from principles about what can be observed and how observations can be combined, rather than starting from a mathematical formalism and asking what it means. This approach has produced interesting insights into why quantum mechanics has the specific structure it does, why probabilities follow the Born rule, why the space of quantum states has the particular geometry of a Hilbert space, but it has not yet delivered a resolution of the measurement problem. The field of quantum foundations, once regarded as a somewhat marginal philosophical pursuit, has become increasingly central to physics. The practical development of quantum technologies has made questions about quantum information, entanglement, and the nature of quantum states genuinely important for engineering, not just philosophy. And the growing sophistication of experiments has made it possible to test ideas about quantum mechanics that previously seemed purely theoretical. This is a genuinely exciting moment for the field, not because answers are imminent, but because the questions are becoming more precise, and the experimental tools for investigating them are becoming more powerful. We are in a period where the boundaries of what can be tested are expanding, and where ideas that were previously beyond experimental reach are becoming testable. The paradoxes will not disappear. They are features of the theory, not bugs, but they may become better understood, transformed from sources of confusion into guideposts toward the deeper theory that eventually resolves them. Consider what Planck's quantum hypothesis looked like in 1900. It was an unexplained assumption, a mathematical trick that worked but made no sense. 50 years later, it was understood as a consequence of a deep theory of matter and light that explained not just the blackbody spectrum, but the structure of atoms, the behavior of materials, the nature of chemical bonds, and the mechanism of nuclear reactions. What looked like an ad hoc patch turned out to be the first visible edge of an entirely new continent of physics. The quantum paradoxes may be serving the same function now. Each one reveals a place where our current description fails. Each failure is information about where the next layer of understanding must go. The exact location of each failure tells you something specific about what the new theory needs to contain. The delayed choice eraser tells you that the new theory needs to handle time and information in a fundamentally different way than classical physics does. Wigner's friend tells you that it needs to handle the relationship between observers and systems without assuming a single objective background reality. The Bell inequality violations tell you that it needs to be non-local in some sense, that what happens at one location cannot be fully described without reference to distant measurements. The black hole information paradox tells you that it needs to reconcile the way quantum mechanics handles information with the way general relativity handles space-time. These are not independent requirements. A theory that satisfied all of them would have to be fundamentally different from anything we currently have. It would have to change our understanding of space, time, information, and probably the meaning of objectivity itself. Whether such a theory is findable, whether human cognition and mathematics are up to the task, is itself an open question. Physicists are optimistic by training and by culture. The history of the field supports optimism. Seemingly impossible barriers have repeatedly fallen before careful thinking, new experimental data, and the willingness to abandon assumptions that seemed indispensable. But it is also possible that some of the paradoxes point to genuine limits. Limits not just of our current theories, but of the kind of understanding science can provide. If reality is fundamentally relational, if properties exist only in the context of interactions, then there may be a sense in which asking what the universe is really like from no vantage point at all is not a question with an answer. This is not a comfortable conclusion, but it is one that some serious thinkers take seriously, and it is one that the quantum paradoxes push toward. Not because physics has run out of things to discover, but because some of the things it might be discovering are limits on the concept of discovery itself. What we can say with confidence is this: the universe is not the mechanical clockwork that Newton described. it is not even the geometric fabric that Einstein described. It is something more complex, more subtle, and more connected than any framework humans have yet assembled. We know this not from speculation, but from experiments, from data, from measurements that have been repeated and verified and checked against every conceivable alternative explanation. The quantum world is real. Its paradoxes are real. And the fact that we find them paradoxical says something not about the universe's failure to make sense, but about our own thinking. Built for a world of medium-sized objects moving at medium speeds, encountering for the first time the behavior of things that do not belong to any familiar category. That encounter is still in its early stages. The paradoxes are the evidence. The research continues. And the universe, indifferent to our confusion, keeps running on whatever rules it actually runs on, waiting for us to figure out what they are. There is one more dimension of the quantum paradoxes worth exploring in depth, and it involves something that most popular accounts of quantum mechanics gloss over: the role of mathematics itself. The reason quantum mechanics is so hard to interpret is not simply that its predictions are counterintuitive, it is that the mathematical formalism is extraordinarily powerful and precise while being almost completely silent on the question of what the formalism represents. When you write down the wave function of an electron, you have a mathematical object, a complex valued function defined over all of space. This function evolves according to the Schrödinger equation in a smooth, deterministic, continuous way. You can calculate from the wave function the probabilities of observing the electron in different positions if you choose to measure it. The calculation is straightforward and its predictions are verified by experiment to extraordinary precision. But what is the wave function? Is it a real physical thing? A field existing in space that carries information about the electron? If so, where does it go when you make a measurement and it collapses? Is it a mathematical tool? A device for organizing and updating probabilities rather than a description of physical reality? If so, what is the physical reality it is implicitly referring to? Is it a description of information, of what any possible observer would know or could know about the system? If so, information from whose perspective, and what makes some things observers and others not? These are not questions that can be settled by doing better experiments with existing quantum mechanics, because every existing experiment is consistent with multiple interpretations. The predictions of quantum mechanics are interpretation independent. The interpretation you adopt is in some sense a metaphysical choice, a choice about what kind of world you think you are living in, that does not change any experimental prediction. Some physicists find this situation acceptable. If the theory works and makes correct predictions, why demand more? This is essentially the Copenhagen attitude: shut up and calculate. Use the formalism, get the predictions, verify them against experiment, and do not ask unanswerable questions about what is happening between measurements. Other physicists find this deeply unsatisfying. Science is supposed to explain what the world is like, not just predict what measurements will show. A theory that explicitly refuses to describe what is happening when no one is looking is not a complete physical theory. It is a calculation recipe. Useful, impressively accurate, but not a description of reality. The tension between these two attitudes has never been resolved, and it runs through every discussion of quantum paradoxes. When you read that physicists disagree about the interpretation of quantum mechanics, what they are really disagreeing about is whether physics is fundamentally about describing reality or about predicting observations. And beneath that disagreement is a deeper one about whether those two goals are necessarily the same. This connects to a debate that has been ongoing in the philosophy of science for well over a century: scientific realism versus instrumentalism. Scientific realism is the view that successful scientific theories are approximately true descriptions of how the world actually is, including the parts of the world that are not directly observable. Electrons are real. Quarks are real. Space-time curvature is real. Even if we cannot see these things directly, the best explanation for why our theories work so well is that they are tracking features of an actual mind-independent reality. Instrumentalism is the view that scientific theories are tools for organizing experience and making predictions, and questions about whether the theoretical entities they posit are real is either unanswerable or meaningless. What matters is whether the theory works, not whether electrons really exist independent of our observations. The wave function might be just a mathematical device that helps us predict what our instruments will report. Quantum mechanics makes this debate especially acute because it is the most successful theory in history and also the one whose connection to an observer-independent reality is most philosophically fraught. Every previous physics, from Newtonian mechanics to electromagnetism to general relativity, was most naturally understood as describing a world that existed independently and was being observed. Quantum mechanics resists that reading in a way that no previous theory did. Part of what makes the measurement problem so persistent is that it is, in some sense, the place where the instrumentalist and realist interpretations diverge most sharply. The instrumentalist can simply say, measurement is what we do when we interact with a quantum system to get a result, and the wave function collapses because we have updated our information about the system. No physical collapse occurs. The wave function was never real. It was just our probability model. This view handles the measurement problem without further mystery. The realist says, if the wave function is not real, what is? There must be some physical description of what the electron is doing between measurements, and that description has to explain why measurement produces a definite result. The realist cannot just say the wave function updates, because that would mean the wave function was never a description of physical reality, which leaves the physical reality unexplained. The many worlds interpretation is an attempt to be fully realist about the wave function. The wave function is real, it never collapses, and all the branches it describes are real. The apparent collapse is an illusion generated by the branching. After a measurement, your branch contains only the outcome you observed, and the other branches are inaccessible. So from within your branch, everything appears definite. This is consistent and avoids the measurement problem in one sense. No physical collapse needs to be explained, but it creates new questions. What determines which branch you end up in? Why do probabilities correspond to the squares of the wave function amplitudes, as the Born rule specifies, if all outcomes occur? How do you make sense of probability in a framework where nothing is random and everything happens? Various attempts to derive the Born rule within many worlds exist, but none are universally accepted. Relational quantum mechanics, as mentioned earlier, takes a different realist path. The wave function is real, but it is real in the same way that velocity is real, as a property of a relationship between two things, rather than a property of one thing in isolation. The electron's state relative to you is real. Its state in absolute terms is not a meaningful concept. Pilot wave theory, also called de Broglie-Bowl mechanics, is another realist interpretation that takes a completely different approach. In this framework, there are actual particles with definite positions at all times. These particles are guided by a real wave function that evolves according to the Schrödinger equation. The wave function is real, the particles are real, and measurement just reveals the pre-existing positions that the wave function has guided the particles to occupy. This restores a fully deterministic picture of reality. If you knew the positions of all the particles and the shape of the wave function, you could, in principle, predict all future observations. The cost is that pilot wave theory is explicitly non-local. The wave function guides all particles simultaneously, and it lives not in ordinary three-dimensional space, but in the abstract configuration space of all possible particle positions. This means that in a system of two entangled particles, the wave function that guides them is defined over the six-dimensional space of possible positions of both particles together, not over the three-dimensional space of each particle separately. Changes to the wave function in one region of configuration space can instantaneously influence the guidance of particles in completely different regions of ordinary space. This non-locality is real and irreducible in pilot wave theory. It is built into the structure of the wave function. Einstein would not have liked it, but it is consistent with the Bell inequality violations, and it makes all the same predictions as standard quantum mechanics. What pilot wave theory lacks is any natural extension to relativistic physics or quantum field theory, the framework we need to describe elementary particles at high energies. Making pilot wave theory compatible with special relativity requires additional assumptions that are not yet fully worked out, and extending it to quantum field theory is an ongoing research challenge. Each interpretation of quantum mechanics has its own strengths and its own blind spots. Each one handles some aspects of the theory naturally and handles others awkwardly. And because all of them reproduce the same experimental predictions, there is no experiment that currently distinguishes between them. The choice of interpretation is genuinely a philosophical choice, constrained by physics but not determined by it. This situation is uncomfortable for scientists trained to believe that data decides questions, and it has led some physicists to dismiss the interpretations debate as irrelevant to real physics. But this dismissal carries its own costs. The interpretation you implicitly adopt affects how you think about problems, what analogies you reach for, what questions seem natural to ask. When physicists are working on quantum gravity or quantum information or the foundations of statistical mechanics, the interpretation framework they are operating within shapes what they take to be the important questions and what they consider adequate answers. The paradoxes we have been exploring are, in a sense, arguments between interpretations made concrete through experimental design. The delayed choice eraser is a concrete demonstration that the Copenhagen strategy of not asking about what happens between measurements has consequences that become explicit when you arrange measurements in the right way. Wigner's friend is a concrete demonstration that the Copenhagen assignment of a classical quantum boundary must be made somewhere, and that wherever you make it, the physics on either side of the boundary looks different. The Bell inequality violations are a concrete demonstration that hidden variable theories of a particular kind cannot reproduce quantum mechanics. These are not just philosophical puzzles, they are constraints on any future theory. Any interpretation, any extension, any modification of quantum mechanics must account for all of these results. The delayed choice eraser must be explainable. Wigner's friend must be handled. Bell violations must come out right. The black hole information paradox must eventually be resolved in a way that preserves quantum mechanical unitarity without breaking general relativity. The constraints are tight, the space of possible solutions is narrowing, and the researchers working in this space are among the most precise thinkers in science, using the most sophisticated mathematical tools available. It would be a mistake to leave this exploration with the impression that progress is not being made. It is. The understanding of quantum entanglement has advanced enormously since Bell's theorem. Quantum information theory has provided new conceptual tools for thinking about what the theory is doing. The AD-SCFT correspondence in string theory has provided concrete evidence that at least in specific mathematical settings, information is preserved through black hole evaporation. Objective collapse models have been experimentally constrained to smaller and smaller parameter ranges. And perhaps most importantly, the conversation between physics and philosophy about what quantum mechanics means has become more rigorous and more productive than it was in the middle of the 20th century, when the Copenhagen instruction to shut up and calculate dominated the culture. Physicists now argue with more precision about interpretation, and philosophers of physics have become sophisticated enough in the technical details to contribute meaningfully to those arguments. The quantum world is not finished revealing itself. The paradoxes we have discussed are probably not the last ones, and may not even be the deepest ones. Every time physicists have thought they were close to the bottom of the stack, another layer has appeared beneath. Atoms, then nuclei, then protons and neutrons, then quarks, then the quantum fields that quarks are excitations of. Each layer revealed new phenomena and new questions that the previous layer could not anticipate. There is no reason to think we have reached the final layer. If anything, the convergence of quantum mechanics and general relativity into an unresolved tension suggests that the next layer might be more radical than any previous one. Something that changes the concept of space or time or information or the observer in ways we have not yet imagined. That unknown territory is not a failure, it is the frontier. And frontiers are where the most interesting things happen. The quantum paradoxes sit at that frontier. They are signs that the territory is real, that there is something there to understand, and that the current maps are incomplete. Every scientist who has worked on these questions has made the map more detailed, even if they have not yet drawn the boundaries of the continent. And every new experiment, every new mathematical result, every new conceptual clarification adds to what will eventually be a complete picture. We are not there yet, but the work of getting there is already one of the great intellectual endeavors of human history. And the destination, whatever it turns out to be, will almost certainly be stranger and more interesting than anything we currently expect. Consider the scale of what quantum mechanics is actually describing when you step back from the paradoxes and look at the full picture. An electron has a mass of roughly 9.1 times 10 to the negative 31 kilograms, which in ordinary language is 910 billionths of a billionth of a billionth of a billionth of a kilogram. If you lined up a billion electrons side by side, the resulting line would be roughly 1 millimeter long. A human body contains roughly 7 billion atoms, and each atom contains electrons, protons, and neutrons, each of which is itself a quantum system described by wave functions and subject to all the strange rules we have been discussing. The classical world we experience, the world of tables and chairs and hands and faces and sunsets, emerges somehow from this enormous collection of quantum systems. Each individual quantum component is in superposition. The combined system of 7 billion atoms, each described by a wave function spread over all of space, somehow produces the definite-looking experience of sitting in a room in a chair with clear boundaries and fixed properties. How this happens is itself an unsolved problem in physics, adjacent to and intertwined with the measurement problem. Decoherence explains why macroscopic objects do not exhibit quantum interference. The quantum correlations that would produce interference are distributed across so many environmental degrees of freedom so rapidly that they become effectively unobservable. But decoherence does not explain why, from your first-person perspective, you always seem to be in one definite world, rather than a superposition of many. This question about the emergence of the classical world from quantum mechanics is sometimes called the macro-objectification problem. It asks, at what scale and through what process do quantum probability clouds become the definite objects of everyday experience? At the level of an electron, superposition is real and observable. At the level of a human body, it is not. Somewhere between an electron and a human, the transition occurs. But where exactly, and why there rather than somewhere else? Schrödinger's original cat paradox was designed to make this question vivid. If a cat is placed in a box with a quantum trigger that has a 50% chance of releasing a lethal mechanism, then, according to the Schrödinger equation, the state of the cat after some time is a superposition of alive and dead. But when you open the box, you see one or the other, not both. The cat is not in superposition. You are not in superposition of having seen a living cat and having seen a dead cat. The definite result appears. The Copenhagen interpretation dissolves this by placing a classical boundary around the cat and saying the quantum description only applies inside the boundary. But this is unsatisfying because the boundary is arbitrary and because the cat itself is made of quantum particles. The many worlds interpretation says the cat is in superposition and the universe has branched. You are in superposition of having opened the box and seen a living cat and having opened the box and seen a dead cat, but each branch does not know about the other. Each version of you has a definite experience within its branch. Objective collapse theories say the cat is not in superposition because systems as large as a cat collapse to definite states in an extremely short time due to the spontaneous collapse mechanism. Pilot wave theory says the cat always had a definite state. It was just the wave function that was in superposition, and the particle positions underlying the cat's physical state were always definite, just following the guidance of the wave function. Each answer has implications that ripple outward. Each makes different predictions about where the quantum classical transition occurs and what it looks like, and each one is being tested against increasingly precise experiments. In recent years, physicists have managed to observe quantum behavior in increasingly large objects. Molecules containing hundreds of atoms have been demonstrated to exhibit quantum interference. Vibrating mechanical structures containing trillions of atoms have been cooled to their quantum ground state and put into superpositions. Quantum effects have been observed in biological systems, including in the light harvesting complexes of certain photosynthesizing bacteria. The quantum classical boundary, wherever it is not as far down the size scale as previously assumed. This experimental progress is exciting for multiple reasons. It means the measurement problem can increasingly be tested, not just debated philosophically. It means the conditions under which decoherence eliminates quantum behavior can be studied precisely, rather than just estimated theoretically. And it means the assumptions built into various interpretations can be checked against data in situations that previous generations of physicists could not have reached. The results so far suggest that quantum behavior persists to larger scales than the Copenhagen intuition implied, and that decoherence, while real and important, does not eliminate quantum mechanics even for quite large systems under the right experimental conditions. This is consistent with many worlds and with objective collapse theories that place the collapse threshold at a scale larger than what has yet been tested. It is not yet consistent or inconsistent with any specific interpretation in a decisive way, but it is narrowing the space of viable options. Meanwhile, in cosmology, quantum mechanics is being forced into contact with questions about the largest scales of the universe. The inflationary model of the early universe, which proposes that the universe underwent a period of extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang, relies on quantum fluctuations as the seeds of all large-scale structure. The galaxies, the galaxy clusters, the cosmic web of filaments and voids that we observe today all trace back to quantum uncertainty in the initial state of the inflaton field, the hypothetical field that drove inflation. If this picture is correct, and the evidence from the cosmic microwave background is strongly consistent with it, then the large-scale structure of the observable universe is essentially a quantum measurement outcome that has been amplified to cosmic scales. The specific arrangement of matter in the universe around us is one branch of what was originally a quantum superposition. The universe we inhabit is, in a very direct sense, an outcome of a quantum event. This raises the Wigner's friend problem at the largest possible scale. Who or what measured the quantum fluctuations in the early universe and selected the particular arrangement of galaxies that we observe? The universe did not have an external observer. It was the entire system. The wave function of the universe was presumably not observed by anything outside itself, because there is no outside. This leads to the formalism of quantum cosmology, pioneered by Hugh Everett, Bryce DeWitt, and others, in which the wave function of the entire universe is described by something called the Wheeler-DeWitt equation. This equation has no external time variable, because time is a feature of the universe that emerges from the internal dynamics, not an external parameter that the universe evolves through. The wave function of the universe does not evolve in time in the ordinary sense. It just exists as a static object in an enormous abstract space, with time as an emergent feature of certain internal correlations. Understanding quantum cosmology requires confronting the measurement problem in a context where there is no possibility of an external observer, and where the usual Copenhagen machinery of drawing a boundary between observer and system breaks down entirely. Every interpretation of quantum mechanics must have something to say about this, and none of them handle it entirely comfortably. The many worlds interpretation was actually motivated in part by this cosmological context. Everett developed it precisely because he wanted a quantum mechanics that could be applied to the entire universe without requiring an external observer. The wave function branches, all branches are real, and cosmology is just the dynamics of the universal wave function playing out across its vast landscape of configurations. But even in many worlds, questions about quantum cosmology are hard. Why does the universe have the particular quantum state it has? What determined the initial conditions of the universal wave function? Is there a natural measure on the space of possible universal wave functions, or are we just picking initial conditions by hand? These questions do not have settled answers. Asking about the initial conditions of the universe is asking about the boundary conditions of everything we can possibly observe, and boundary conditions are, in some sense, always imposed from outside the system, but there is no outside the universe. So either the initial conditions of the universe were not imposed, but somehow self-selecting, or they were randomly drawn from some distribution we do not understand, or they have some deep physical explanation that current physics cannot provide. Stephen Hawking and James Hartle proposed one approach in the 1980s called the no-boundary proposal. They suggested that the universe emerged in a way that was analogous to the surface of a sphere, where there is no boundary, no edge, and no beginning. Just as you can traverse the surface of a sphere and never reach an edge, the universe has a quantum history that is finite but unbounded. The concepts of beginning and end dissolve in the quantum gravitational picture, replaced by a smooth, compact geometry in imaginary time. This is mathematically intriguing and has been the subject of much subsequent work, including significant debates about whether it actually produces a reasonable probability distribution for the early universe. The debates continue, and the proposal has both strong advocates and strong critics. What all of this illustrates is that quantum mechanics does not stop being strange when you zoom out. The paradoxes at the level of single particles scale up, in modified and amplified forms, to the level of the entire universe. The measurement problem becomes the problem of quantum cosmology. Wigner's friend becomes the problem of the observer in cosmology. The black hole information paradox becomes the problem of what happens to information at the boundaries of spacetime, including at the beginning and possibly the end of the universe. The quantum world is not a small corner of physics that specialists worry about while the rest of science proceeds normally. It is the foundation on which all of physics rests, and the paradoxes at its foundation propagate upward through every scale. This is both daunting and clarifying. Daunting because the problems are genuinely hard and the stakes are high. Clarifying because it means that progress on the foundations of quantum mechanics is not an isolated technical achievement. It is progress toward understanding what kind of universe we actually inhabit. A universe that has been running on quantum rules for 14 billion years, producing everything from hydrogen atoms to neutron stars to the neurons firing in your brain as you process these ideas. The fact that we do not fully understand those rules is not a reason for despair. It is a reminder that the universe is richer and stranger than any framework we have built so far. And if history is any guide, the frameworks that replace the current ones will not simplify the picture, but will reveal new layers of structure and new categories of phenomena that were invisible from within the previous understanding. Quantum mechanics revealed that the solid, deterministic, clockwork universe of Newton was an approximation. General relativity revealed that space and time were not fixed backgrounds, but dynamic participants in the physics they contained. Whatever comes next will reveal something about the current picture that we cannot yet see from inside it, something that will make the paradoxes seem not strange but obvious in retrospect, and that will open new paradoxes we have not yet imagined. Science does not end with solved problems. It ends at the current edge of what is known and what can be asked, and that edge is always moving. The quantum paradoxes are where that edge currently sits, and the people working at that edge, running the experiments, deriving the theorems, building the mathematical frameworks, arguing about the interpretations, are doing what scientists have always done at the most productive moments in the history of the field. They are sitting with the paradoxes and refusing to look away. There is a thought experiment that rarely makes it into popular accounts of quantum mechanics, but that physicists working on foundations consider one of the most revealing, the quantum Zeno effect. The name comes from the ancient Greek philosopher Zeno of Elea, who proposed a series of paradoxes about motion. The most famous involves Achilles and a tortoise. Achilles gives the tortoise a head start in a race. By the time Achilles reaches where the tortoise started, the tortoise has moved forward. By the time Achilles reaches that new position, the tortoise has moved again, and so on, infinitely. Zeno argued that Achilles could never actually catch the tortoise, because there are infinitely many intervals of space to cross, and each takes some time. Of course, Achilles does catch the tortoise. The resolution involves convergent infinite series, and the paradox is really an argument about the nature of infinity and continuity rather than an actual physical impossibility. But Zeno's name has been attached to a genuinely strange quantum phenomenon that echoes the structure of his original paradox. In quantum mechanics, an unstable particle decays over time. A radioactive nucleus will, with some probability, emit radiation and transform into a different nucleus. The probability of decay grows with time, following a characteristic exponential curve. After one half-life, half the nuclei in a large sample have decayed. After two half-lives, 3/4, and so on. Now, what happens if you keep measuring the particle extremely frequently to check whether it has decayed? According to quantum mechanics, each measurement collapses the wave function and resets the probability of decay. If you measure fast enough, you continually reset the particle to its undecayed state, and the decay is dramatically suppressed. In the limit of continuous observation, the particle would never decay at all. This is the quantum Zeno effect, and it has been confirmed experimentally. Atoms being observed continuously through laser illumination have been shown to remain in their initial state far longer than they would without observation, exactly as quantum mechanics predicts. The inverse also exists, the quantum anti-Zeno effect, where measuring at a particular intermediate frequency can actually accelerate decay. Whether you speed up or slow down the decay depends on the specifics of the energy spectrum and how the measurement frequency relates to it. Both effects are now used in quantum information applications, where the ability to control decay rates through observation frequency is valuable for maintaining quantum states long enough to perform computations on them. But the Zeno effect also has deep implications for the measurement problem. It shows that measurement is not just a passive revelation of a pre-existing fact. It is an active intervention that reshapes the physical evolution of the system. The system evolves one way when observed and differently when not. This is not just about our knowledge updating, it is about the physics actually being different. In classical physics, this makes no sense. A nucleus decays or does not decay. Watching it does not change what it does. In quantum mechanics, the evolution of the system is entangled with the measurement process in a way that cannot be separated. The observer is not outside the system looking in, the observer is part of the dynamical picture. This is one of the reasons why the quantum Zeno effect is philosophically significant beyond its practical applications. It makes experimentally concrete what is otherwise an abstract claim. In quantum mechanics, observation has physical consequences. The act of looking changes what happens. Combined with the delayed choice eraser, which shows that deciding when to look can apparently influence what already happened. The Zeno effect rounds out a picture in which the observer's role in quantum mechanics is genuinely dynamic, not just epistemic. This is exactly what the measurement problem is pointing at, and the Zeno effect demonstrates it in a controlled, repeatable way that leaves little room for alternative explanations. Another experimental area that pushes at the foundations of quantum mechanics is quantum contextuality. This is a subtler concept than entanglement, but in some ways even more fundamental. In classical physics, the value of a physical quantity is independent of how you choose to measure it. If you want to know the temperature of a cup of coffee, you can use a thermometer, a thermocouple, a pyrometer, or any other method, and you will get the same answer because the temperature is a property of the coffee, not a property of the interaction between you and the coffee. Quantum mechanics violates this assumption in a specific mathematical sense. The value of a quantum observable can depend not just on the system being measured, but on the context of the measurement, specifically on which other compatible observables are being measured simultaneously. Two different measurement setups, both of which include a measurement of the same quantity, can yield different distributions of results for that quantity, even though the quantity is the same. This was established through the Cauchy-Specker theorem, proved in 1967, which showed that quantum mechanics cannot be reproduced by any model in which all observables have pre-assigned context-independent values. No matter what hidden variables you hypothesize, you cannot assign definite values to all quantum observables simultaneously without creating contradictions. Measurement context is inescapable. Quantum contextuality has been confirmed experimentally and is now understood to be a resource for certain quantum information tasks. It is related to but distinct from entanglement, and in some computational contexts, it appears to be the key property that gives quantum computers advantages over classical ones. For our purposes, the significance of contextuality is that it deepens the strangeness of the measurement problem. Properties in quantum mechanics are not just unknown before measurement. In a precise mathematical sense, they cannot all exist simultaneously in a way that is independent of how they are measured. The structure of quantum observables is such that you cannot consistently assign them all definite values at once. Measurement does not just reveal, it participates in determining. This has led some physicists to adopt what is sometimes called a relational or perspectival view of quantum properties, where the properties of a system are always defined relative to a reference frame or a context of interaction rather than existing absolutely. This is conceptually close to Ravelli's relational quantum mechanics, but arrives at a similar place from a different direction, through the mathematics of contextuality rather than through philosophical analysis of what measurement means. The connection between contextuality and quantum advantage in computation is currently one of the most active areas of research at the intersection of quantum foundations and quantum information. If you can identify exactly which quantum features are responsible for computational advantages, you can potentially engineer systems that exploit those features more deliberately. And if the answer turns out to be contextuality, that would mean the practical advantage of quantum computers is traceable directly to the measurement problem, to the fact that quantum observables do not have context-independent values. This would be a remarkable connection between the deepest philosophical puzzles of quantum mechanics and the most practical technological applications. The paradoxes would not just be curiosities but engines of capability. There is also ongoing work connecting quantum mechanics to thermodynamics and statistical mechanics, which raises its own deep questions. Thermodynamics is the science of heat and energy flow, and its most fundamental principle, the second law, says that entropy, a measure of disorder or information loss, always increases in a closed system. Things naturally move from ordered states to disordered ones. Heat flows from hot to cold. You cannot run a heat engine with perfect efficiency. The second law defines the arrow of time that is so conspicuously absent from the fundamental equations of physics. The Schrödinger equation is time-symmetric. Newton's laws are time-symmetric. Maxwell's equations are time-symmetric. But the second law is not. It points time in one direction, the direction in which entropy increases. Where does this arrow come from? If the fundamental laws are time-symmetric, why does the macroscopic world have a preferred direction of time? The conventional answer involves initial conditions. The early universe was in an extremely low entropy state, something close to a smooth, ordered distribution of matter and energy. Everything that has happened since then has been the universe relaxing from that improbable initial state toward higher entropy. The arrow of time exists not because the laws favor one direction, but because the initial conditions of the universe were special. But this answer raises its own questions. Why were the initial conditions special? What process selected a low entropy beginning? And if the laws of physics are time symmetric, what happens at the quantum level when we try to reverse time? In quantum mechanics, the time reversal of a process is another valid quantum process. You can, in principle, reverse the evolution of a quantum system, taking it back to an earlier state. Implementing this experimentally is extremely hard, requiring exquisite control over all degrees of freedom. But it is not forbidden. And in principle, if you could reverse the evolution of an entire macroscopic system, including all its environmental entanglements, you would see entropy decrease. The broken egg would reassemble. The reason this never happens in practice is that macroscopic systems have an astronomically large number of degrees of freedom, and the environmental entanglements that support decoherence spread quantum correlations across so many particles so quickly that reversing the process would require tracking and controlling information at a level of precision that is physically impossible given the size of the system. But this explanation is quantitative, not qualitative. It tells you that reversing macroscopic processes is overwhelmingly unlikely, not that it is impossible in principle. The arrow of time is a statistical consequence of initial conditions and system size, not a fundamental asymmetry in the laws. This is deeply connected to the quantum information perspective on black holes. If information is conserved in quantum mechanics, then the evolution of the universe is in principle reversible. If you had complete information about the current quantum state of the universe and the laws of physics, you could run the movie backward and see the past. This is the quantum mechanical version of Laplace's demon, the hypothetical intellect that Newton's determinism implied could predict all future and retrodict all past from the current state. In quantum mechanics, the demon cannot know the exact current state due to Heisenberg's uncertainty principle, and cannot know it without disturbing it. But the formal reversibility is still there in the mathematics. The wave function evolves unitarily, and unitary evolution is reversible. The black hole information paradox is, in part, an argument about whether this formal reversibility holds when gravity is included. If information truly disappears into black holes, then the evolution of the universe is not reversible even in principle, and the fundamental quantum mechanical property of unitarity fails. Hawking's original calculation suggested that it did fail, and this is what created the paradox. Recent work suggests that unitarity is preserved, that information does escape through Hawking radiation in a subtle form, and that the apparent information loss was an artifact of using classical spacetime where quantum geometry is needed. But even if the information paradox is resolved, the connection between quantum mechanics, thermodynamics, and the arrow of time remains a deep and incompletely understood area. The statistical mechanics of quantum systems, the quantum origins of thermal equilibrium, the quantum formulation of entropy, and the precise relationship between quantum coherence and the second law are all active research topics with genuine open questions. Physics is richer than any single paradox, and the quantum paradoxes we have explored are connected to each other and to broader questions across the entire range of physics, from the smallest particles to the largest structures in the universe. What unifies them all is the sense of standing at an edge. The experiments point one way, the intuitions point another. The mathematics describe something that the concepts cannot fully capture. And in that gap between description and understanding lies the most interesting territory in all of contemporary physics. The physicists working in that territory are not chasing something they expect to find easily. They are working on problems that have resisted resolution for decades, using tools that are the most powerful ever developed, pushing toward answers that may require abandoning assumptions so basic they are barely recognized as assumptions. The speed of light as an absolute limit, the primacy of locality, the independence of observer and system, the fixed topology of spacetime, the very concept of a particle. Any of these might turn out to be negotiable. Any of them might be revealed by the right experiment or the right theoretical insight to be an approximation that works at our scale but breaks down at the scales where quantum and gravity meet. And when that happens, the paradoxes will not disappear. They will be understood. The things that look like contradictions from within the current framework will look like clues from within the next one. The strangeness will not go away, but it will be recognized as the fingerprint of something deeper rather than the sign of something broken. That is what makes physics worth doing. Not the accumulation of facts, though facts matter. Not the construction of technology, though technology matters. But the process of finding out that the universe is different from what you thought, that the categories you used to organize your thinking were adequate for one domain and inadequate for another, and that there is always another domain waiting. Quantum mechanics opened that door a century ago and has not finished walking through it. The paradoxes are the evidence, the research is the response, and the universe, as always, is waiting to see what we make of it. One final thread worth tracing is the relationship between quantum mechanics and the nature of consciousness itself, which appears at the edges of several of the paradoxes we have explored. The measurement problem asks what counts as an observer. Wigner's friend asks whether two observers can have different realities. Quantum suicide asks what happens to subjective experience across branching worlds. These questions brush up against one of the deepest unresolved problems in all of science and philosophy: the nature of consciousness and its relationship to the physical world. The standard scientific position is that consciousness is a product of physical processes in the brain, that it arises from the information processing performed by neurons and their connections, and that it is in principle fully explicable in terms of physical science, even if the details remain unclear. This position is called physicalism or materialism, and it is the working assumption of most scientists. But quantum mechanics creates an unusual situation for this assumption. If consciousness is a physical process, and physical processes are governed by quantum mechanics, then consciousness is in some sense a quantum process. The neurons in the brain are molecular structures subject to quantum mechanical laws. The chemical reactions that underlie thought, memory, and perception involve electrons, atoms, and molecules, all of which are quantum systems. Whether quantum mechanics plays any specific functional role in consciousness, beyond the background fact that all matter is quantum mechanical, is a hotly contested question. The physicist Roger Penrose and the anesthesiologist Stuart Hameroff have proposed a specific theory called orchestrated objective reduction, or OR, in which quantum computation occurring in structures inside neurons called microtubules plays an essential role in generating conscious experience. In this view, consciousness is not just a quantum process in the trivial sense that all matter is quantum mechanical, but involves a non-computable quantum physical process specifically tied to the proposed objective reduction of wave functions. Most neuroscientists and physicists are skeptical of this proposal. The thermal noise in the warm, wet environment of the brain is generally thought to be far too large to allow the kind of coherent quantum computation that OR requires. Decoherence would destroy any quantum superposition in neurons in an extraordinarily short time, far shorter than any relevant timescale for neural processing. But the question of whether quantum mechanics plays any specific role in consciousness is separate from the question of whether consciousness plays any specific role in quantum mechanics. And it is the second question that the measurement problem most directly raises. If the Copenhagen interpretation is taken seriously as a statement about reality rather than just as a calculation tool, it implies that properties do not exist until they are observed. The observer plays a role in actualizing the physical world. This does not necessarily mean consciousness is special in quantum mechanics, because the Copenhagen interpretation does not define observer as a conscious observer, but just as an apparatus or system that has performed a measurement. A photodetector counts as an observer. A thermostat counts as an observer, but the boundary between what counts as a measurement and what does not is never precisely specified in Copenhagen quantum mechanics, and this ambiguity allows the question to persist. If a thermostat counts as an observer, then all of physics proceeds without requiring consciousness. But if what ultimately counts as an observation must terminate in a conscious mind, then consciousness is doing real work in the physical world, not just passively experiencing it. The physicist John von Neumann formalized this issue in his mathematical treatment of quantum mechanics, where he showed that the chain of physical interactions that constitutes a measurement can be placed at different points without changing the observable predictions. The quantum mechanical description of the measuring apparatus can be extended to include the apparatus, and then extended further to include the observer's body, and further still to include the observer's brain and nervous system. At what point does the quantum description give way to the classical description? Von Neumann's formalism did not specify, and without a specification, you could push the boundary all the way to the observer's conscious experience without any inconsistency in the math. This is sometimes called the von Neumann-Wigner interpretation. and it holds that the wave function collapses when, and only when, it enters the consciousness of an observer. This view has been unpopular among physicists for reasons mentioned earlier. It is vague about what consciousness is, it introduces non-physical elements into physics, and it has a somewhat solipsistic flavor. But it is logically consistent with quantum mechanics and cannot be straightforwardly ruled out by experiment. What would rule it out is a demonstration that wave function collapse occurs in systems that are definitively not conscious. Objective collapse theories, if they are correct, would show that collapse happens spontaneously as a physical process with no reference to observers or consciousness. The ongoing experimental tests of objective collapse theories are, therefore, in a sense, also tests of whether consciousness plays any special role in quantum mechanics. If objective collapse is confirmed, consciousness is irrelevant to the physics. The wave function collapses on its own, driven by a physical mechanism that applies equally to observed and unobserved systems. Quantum mechanics would turn out to be a theory of matter that has nothing special to say about the observer. If objective collapse is ruled out by experiment, and if the many worlds interpretation is adopted, then consciousness is also irrelevant in a different sense. Everything happens, all branches are real, and consciousness just happens to be located in one branch rather than another without playing any causal role in determining which. But if objective collapse is ruled out and many worlds is unsatisfying, and if the measurement problem remains genuinely unresolved, then the consciousness plays a role interpretation stays in the running as an option that cannot be dismissed. This is a peculiar situation for science. The exact role of the observer, and whether that role involves consciousness in a physically specific sense, is not yet decided by either experiment or theory. And the question touches on one of the oldest philosophical puzzles: the relationship between mind and world, between the knower and the known, between the subject and the object. Quantum mechanics did not create this puzzle. Philosophers have wrestled with it since long before physics was a discipline, but quantum mechanics gave it a new and strikingly precise form. In classical physics, the observer could always in principle be treated as part of the system and described by the same physics as everything else. The observer was just more matter, governed by the same deterministic laws. In quantum mechanics, the observer's role in collapsing the wave function, real or apparent, creates an asymmetry that classical physics never had. Whether this asymmetry is fundamental or will be resolved by a better theory, and whether its resolution requires including consciousness in the physics or excluding it, remains one of the genuinely open questions of the field. What is clear is that the question matters. How we answer it affects how we think about the relationship between science and experience, between the third-person description of the physical world and the first-person reality of being alive and aware inside that world. It is a question that has implications not just for physics, but for everything built on top of physics, including biology, neuroscience, psychology, and the deepest questions about who and what we are. The quantum paradoxes bring us, ultimately, to this. Not because quantum mechanics is about consciousness, but because the attempt to understand quantum mechanics with full rigor eventually forces a confrontation with what we mean by knowing, by observing, by experiencing. The theory that describes matter at its most fundamental level keeps bumping into the fact of the observer. And the observer is not just a machine for recording data, it is the thing through which all of physics, all of science, all of human understanding happens. What the quantum paradoxes are telling us, at their deepest level, is that we cannot fully understand the universe without including the understander. Not as a mystical claim, but as a precise scientific statement. The formalism of quantum mechanics cannot be cleanly completed without specifying what counts as an observation, and any specification of what counts as an observation eventually has to grapple with the nature of observers. That is an uncomfortable place to end up if you want a physics that is purely objective, purely third person, purely about the world out there independent of anyone looking at it. But it may be the most honest description of where the physics actually leads. The universe is not making things easy for us. It has given us a theory that works beautifully and leaves the deepest questions open. A theory that describes the smallest constituents of reality with extraordinary precision and refuses to say clearly what those constituents are or what happens to them when we are not looking. A theory that predicts the outcomes of experiments to many decimal places and cannot fully explain how outcomes happen at all. This is not a failure of science. It is science in its most alive and productive state, finding the edges of what is known, characterizing those edges precisely enough to point toward what might lie beyond them, and maintaining the intellectual honesty to say that the questions are real and the answers are not yet in. The history of physics suggests that the answers will come. They always have, in some form, even if the form was radically different from what anyone expected. And when they come, they will not make the universe less strange. They will reveal new strangeness beneath the current level, new questions, sharper and more interesting than the ones that preceded them. The quantum paradoxes are not the final word. They are the current frontier. And frontiers, by their nature, are where the most interesting things happen. If the ideas in this video made you think in new ways about what the universe is and how we know it, share it with someone who might find it equally puzzling. The best conversations start from questions nobody can fully answer yet. And on that score, quantum mechanics has never run short of material. And yet, for all the uncertainty, there is something clarifying about quantum mechanics when you sit with it long enough. The paradoxes stop feeling like failures and start feeling like features. Not bugs in our understanding, but glimpses of a deeper order that our current mathematics is only approximating. Consider the double slit experiment one more time, not as a puzzle, but as a fact. A single particle, fired one at a time, builds up an interference pattern over thousands of repetitions. Each individual particle arrives at a specific point, making a single dot on the screen. No single arrival looks like interference. Only the accumulated pattern, built from thousands of individual events, reveals the wave structure. The wave is not carried by any individual particle. It exists in the statistics, in the collective behavior, in the relationship between many events rather than in any one event. This suggests something profound. The wave function may not be a property of individual particles, it may be a property of ensembles, of possibilities, of potential measurement records. The particle is not a little ball with a wave function attached. The particle is what the wave function describes when you ask, "What will I find if I look here?" The particle is the answer to a question, not a thing that exists prior to the question being asked. This is not mysticism. It is a precise statement about what quantum formalism actually says when you trace its implications carefully. The wave function is not a physical field in space, like an electromagnetic field. It is a function over the space of possible configurations, and configurations only become actual through interaction. The particle comes into being in the sense of having a definite position only when it interacts with a position-sensitive system. Before that interaction, position is not undefined or unknown. It is genuinely not a feature of the situation. If this reading is correct, then the quantum world is not a world of things, but a world of processes and relations. The building blocks of reality are not particles sitting in space, but events, interactions, processes of becoming. Space itself may be secondary, a framework that emerges from the statistical structure of interactions rather than a container in which interactions occur. This resonates with ideas in other parts of physics. In general relativity, space-time is not a fixed background, but a dynamic entity that curves in response to matter and energy. In thermodynamics, temperature and pressure are not properties of individual molecules, but emergent features of large collections. In information theory, the content of a message is not a property of the symbols, but of the relationship between sender and receiver. Across physics, the trend is toward understanding properties as relational rather than intrinsic, as arising from context rather than being carried independently. Quantum mechanics fits into this trend in the most radical way possible. It suggests that even position, even the definite location of a particle in space, is not an intrinsic property but a relational one, defined by the interaction between the particle and a measuring apparatus. And if position is relational, then the space it is a position in may also be relational, not a fixed container, but an emergent structure that arises from the pattern of quantum interactions. This is speculative. It is not established physics, but it is speculative in a direction that is consistent with everything we currently know and that might, if correct, dissolve several paradoxes simultaneously. If space is emergent, the non-locality of entanglement becomes less surprising. The entangled particles are not really separated in some more fundamental description, even though they appear separated in the emergent spatial picture. If time is emergent, the time symmetry of quantum mechanics and the apparent retrocausality of the delayed choice eraser become less mysterious. The past and future are not fundamentally different in the underlying description, even though they appear asymmetric in the emergent temporal picture. None of this resolves the measurement problem. Emergence does not tell you what triggers the emergence of a definite outcome from a superposition of possibilities. but it might change the form of the question. Instead of asking how a quantum system collapses from many possibilities to one outcome, you might ask how the pattern of interactions that constitutes an observation generates the emergent fact of a definite outcome. The question becomes about dynamics and structure, rather than about a mysterious collapse event. Whether that reframing helps or just relocates the mystery is not yet clear, but it illustrates the kind of conceptual work that physicists and philosophers are doing, not just calculating within an existing framework, but trying to identify which concepts in the existing framework are load-bearing and which might be scaffolding that can be removed once the building underneath is better understood. The quantum paradoxes are part of that process of removal. Each one identifies a place where a concept that seemed fundamental might actually be contingent. The paradoxes of time suggest that the arrow of time and the asymmetry of past and future might be emergent rather than fundamental. The paradoxes of observation suggest that the observer-world boundary might be an approximation rather than a hard line. The paradoxes of entanglement suggest that spatial separation might be less fundamental than it appears. The black hole information paradox suggests that the space-time geometry of general relativity might be an emergent approximation to something more fundamental. All of this is consistent with the history of physics, in which each major theoretical advance revealed that concepts previously considered fundamental were in fact derived. Absolute time, which Newton took as fundamental, turned out to be a limiting case of relativistic spacetime. The ether, which 19th century physicists took as fundamental, turned out to be unnecessary. The deterministic trajectory of classical mechanics, which seemed to follow inevitably from Newton's laws, turned out to be a macroscopic approximation to quantum probability. Each time, something that seemed load-bearing turned out to be scaffolding, and each time, the structure that remained after the scaffolding was removed was more elegant, more unified, and more accurately predictive than what came before. The expectation that something similar will happen again with quantum mechanics is not wishful thinking. It is extrapolation from a pattern that has repeated consistently. The pattern does not guarantee the next step, but it makes the next step plausible and makes the effort of looking for it worthwhile. So when you encounter quantum paradoxes, the right response is not to dismiss them as too abstract or to accept them as mysterious facts about a universe beyond comprehension. The right response is the one that physicists bring to them every day. Take them seriously as clues, work out their implications carefully, design experiments that can distinguish between competing explanations, and remain genuinely open to the possibility that the concepts you started with may not survive contact with the deeper answer. The universe has been running for nearly 14 billion years on whatever rules it actually runs on. We have been trying to figure out those rules for a few centuries, and our current best description is both extraordinarily accurate and demonstrably incomplete. The incompleteness is not an embarrassment, it is an invitation. The quantum paradoxes are that invitation, written in the language of experimental results, mathematical theorems, and thought experiments that have been verified and sharpened over a century of work. They are the universe's way of telling us that we are close to something important, that the next layer is within reach if we look carefully enough, and that the most interesting questions are still ahead. That is not a frustrating place to be. That is the best possible place for physics to be. And the fact that we can see the paradoxes clearly enough to articulate them precisely is itself a form of progress. A century ago, these questions could not have been posed this sharply. A century from now, someone may look back at our current confusion the way we look back at pre-quantum physicists confidently predicting infinite radiation from heated objects, as a sign of how much there was still to learn, and as evidence of how far knowledge can travel when driven by curiosity, precision, and the refusal to be satisfied with answers that do not quite fit. The universe is under no obligation to make sense to us. The fact that it has, so far, responded to every serious investigation with patterns that yield to mathematical description is remarkable and not at all guaranteed to continue. But it has continued through every previous transformation of physics, and there is no obvious reason why it should stop now. The quantum paradoxes are not the end of the road. They are a sign that the road continues through territory we have not yet mapped, toward a destination that will be stranger and more illuminating than anything we currently expect. Stay curious, stay uncertain, and keep looking.